The Alternative Natural Philosophy Association presents Clive Kilmister, Ted Bastin and David McGoveran in conversation during the month of December 1992. The recording took place in Cambridge.
Dirac, whom I think of as being one of the most orthodox of orthodox physicists, he was concerned about the fine structure constant and held that quantum electrodynamics was incomplete because the perturbation solutions relied on the fine structure constant having that value, and yet it didn't calculate the value.
Right.
So if Dirac could be worried that way, I feel that more physicists ought to be. Sorry, Ted, what was that?
I say if Dirac could be worried about that, anybody could.
Yes, anybody. Well, anybody ought to be.
Yes,
Yes,
anybody ought to be. Yes, well, that Dirac's position on that's very important because it's the normal point of view is that the discrete basic constants of quantum theory just have the values they do because they have to have some values, and there's nothing to explain. It's a sort of I suppose if you press the people, I'd have to say, well, they were just created like that, or something. Which, getting into a theistic position, which they certainly wouldn't admit to. But really, that's what it does boil down to.
My main motive in the last few years has been the question of the scale constants. Why should they have these values? And I think I owe this to Ted, who had insisted on it many years ago. I think that one of the things that I haven't managed to get clear up till now, but hope to in the future, is that Ted's emphasis has often been on there being limits to observed quantities. For example, if you suppose, let's suppose Planck's constant is known, then the value of the fine structure constant gives you a limit on the smallness of charges that you measure. It can only be the electron charge. And then you can see the same kind of thing in terms of the speed of light because there's a limit on measured velocities, and that's what's all tied up in this theoretical framework of special relativity. I'm not yet in a position to see those two limits as the same kind of thing. One of them originates from the fine structure constant having the numerical value that it does. The other one doesn't in the way that I've constructed it, though I would hope to find a theory in which these two kinds of limit all come under the same guise.
So which being the other?
Well, the speed of light. I mean, that seems to me to present a slightly different problem. I suppose I could put that crudely by saying it's a dimensional quantity, but that I wouldn't really want to put it that way.
Well, so are M and H.
Sure, but
and E.
Yes, but but then the fine structure constant isn't dimensional.
Right, so hence it's
and
important.
so one can have hope, which I feel we're justifying. One can have hope in calculating that number.
Suppose I think we ought to try and go into a bit of detail at this point.
Now we're all happy about this. Okay, that's 137, or maybe a bit different, and we can point something. So now, what we've got to do, we've got to see whether this search can go on and swallow up its own tail, as it were, to bring in some other constants. Well, my guess is then that we want to bring in G, and a tidy way of doing this would be to look at the ratio of G, the gravitational force between the electron and proton in the hydrogen atom, and the ratio of that to the electrical force between them. So we'd get a value for this. Okay, and that's, 10 to the minus 38 or something because of the way up I've put it. The numbers don't matter. I'm just making the bold assumption here that we'll have a wonderful theory in which we get all the numbers. There's a question of what we can get out of it. So now, if one puts up, what have you got? You've imported so far H cross, C, E, big G, MP and ME. So we've got 6 things which we've imported and 2 relations between them. Well, 2 relations, but we're allowed 3 more to determine mass length and time. So that would bring us up to 5, but we're still missing something. So what's the suggestion that we should do? Well, my worry is if you go on and bring in, say, the strong coupling constant, and suppose you found that. Well then, but you brought in the strong coupling constant as well, so that's an additional one, and you bring in another relation, but you lose one. I'm not sure which of you are.
But you lose one? How do you lose
I mean,
one?
suppose you bring in strong coupling then. What shall be the letter that I use for it?
Well, usually it's alpha sub S.
Okay. So you have an alpha sub S, which...
all right, and an alpha sub W.
Which... all right. But now, so you get a number for that. It's been made dimensionless by means of the H cross C and so on. All right. So you have a number, whatever it is, but now the number of things we've got here is, well, this alpha sub S consists of it's H cross C over something else squared, often G squared, isn't it?
Yes.
Right. So now there's a little G here as well, and so this extra equation hasn't helped us. We've now gone up to 7 constants, and we've got 6 relations, and every new one is going.
Except that these are not dimensionless constants, and they could actually be broken up into even that number is not by any means a given. That is the number of constants that you're increasing by that are not dimensionless.
Yeah.
Right.
But doesn't that make matters even worse?
No, because I think what you're referring to is the complexity of current physical theory, not the complexity of our theory. All that you're doing is saying, well, we have a number of dimensionless constants, and these relate in various ways to dimensional constants known in current practice.
Yeah.
We would really be very happy to do without those dimensional ones.
Yes.
But this is how they relate. Yeah. And so what you've got in the box over here, to my way of thinking, is largely superfluous information. It is information about a particular interpretation of the theory that is outside that box.
I think what maybe this is a correct translation of what you're saying, that I ought to have drawn a line there. This is part of the complexity which I don't want to get into. Now I've got those 2 relations. I ought not to bring in any other things like strong interaction constants. I ought to be content with the ones I've got here. And I suppose that the answer might be that I need an MP over ME there. If I have a value for that, say by Frederick's calculation or by Eddington's quadratic or some other such way. So then I have that, and I know that's 1836 by some magical means. Now that would strike out the MP, well, no, now I haven't got that G there, I've got 6 numbers, 3 relations here, and 3 relations which determine the units of mass length and time. So that ought to be the answer to what you were saying, Ted, that you had failed to do. I think we have managed to do it on the board. I feel embarrassed. I feel embarrassed at that situation because it sounds so much like Pierre saying, "No, well, we have done it. We have done it. Yeah, and here it is, and it all comes out." But I think it is that if one has those three relations, and this one we're fairly confident about. This one is fairly straightforward. That one I'm still rather worried about, notwithstanding your improvement of Frederick, but at least there's optimism. Those three, together with something which determines the units, does answer the question we've been raising.
That here you can see how some of the traditional physics sort of becomes unessential. That is the breakout into these various variables like m sub p and m sub e and so on are not absolutely essential to the structure. But I think the same thing will be true as you bring in the structure constant for the strong force and for the weak force and so on, and that you have to do that, and then those necessarily bring in other masses as well, and so you're going to need the other mass ratios. But I think it's really important to differentiate between what was going on that side of the chart and what's on this side, because these things are part of what Pierre and I started out at one point calling laboratory physics, and whereas that's a whole new description of physical theory, and the fact that it's been written that way is for comparison purposes. I would think.
Right.
You know, it's not
Right.
for it's not because you have to solve for those per se. It's not because they have any intrinsic meaning in their own right. It's a way that in a laboratory you happen to have set up a series of experiments and derived some quantities, measured some quantities. It doesn't say that you have to have done laboratory experiments that way. You might have just as easily have done laboratory experiments that led you to 137 without any knowledge ever of h bar c and u squared.
Right.
Certainly, yes.
Yes.
So I think conceptually it's just important to keep those two things distinct. And,
Yes, I agree, but with a slight reservation, because that putting it that way seems to me to cover up one of the problems which our approach burdens us with, and that is this. We're interested in these scale constants. We want to understand how it is that there are these things. One way of putting meaning into that sentence, understand how, would be to calculate them. And we are making some progress, particularly over alpha. Now, the problem which confronts one when calculating alpha is that people will say, oh, you've got 137, or maybe even better. How do you know that's anything to do with h cross c over e squared? And the only answer which one can possibly make to that, I think, is to say, you've put the question the wrong way round. The scale constants are the logically prior things, and that's why we've come to them like this from the theory. The h cross and the c and the e squared are logically derived things, which, okay. What I'd like to show you now is the details which come out of the actual calculation, or rather the principles and the results, without going into the sticky details. The first way I had of looking at it, which is based very much on your sort of thing and which I corresponded to you about, was like this, that I think, well, now we're talking here about the process getting back to somewhere where it was before. When I say so, I mean I'm using rather emotive words like somewhere where it was before. What I mean is a whole sequence of things is coming back as it was, and I'm looking at individual elements of that sequence. Suppose I were to put, quite artificially at this stage, a constraint on the system that it wouldn't go up above level 2. To specify what I mean, you know, the cumulative number of elements at different levels are 3, 10 and 137, and then, oh, I meant level 3 when I never know how to, we always have this systematic ambiguity.
Numbering from 0 or numbering from 1.
That's right. And then it's really level 4, which has about 10 to the 38 elements. So I'm saying, suppose I constrain the system to stop at that point, at level 3, I should say. And then with this totally artificial constraint, which is here meant to be a constraint only in the argument. I mean, I don't mean there is a physical situation in which this happens necessarily. I can look at what's happening and say, well, here's another element coming along. Which one of those is it going to be? It could be any of them, using the ergodic principle. So the probability that it's that one is, of course, 1 over 137. Because the ergodic principle says it was equally likely to be any of that lot. The fact they're at different levels doesn't worry me, because I insist on this systematic level ambiguity. So the number which had been simply pointed to as a scale constant here now appears as a probability. Then I say, oh well, yes, all right, that was a use of this totally artificial constraint to understand what I was doing. But how do I know that the thing is going to be at as high as that level? Or perhaps it would be higher, or perhaps lower. So what I ought to do is not look at this 1 over 137, but ask myself the question, here is this object. What's the chance that it may be at level 1? Well, applying the ergodic principle again, independently of the one I've just talked about, the chance that it might be at level 1, it could be one of the 3 elements there, or equally none of them. That's 4 possibilities altogether. So there's 3/4 of a chance that it's at level 1 and 1/4 that it isn't. So there's a 1/4 of a chance that it's not at level 1. And in that 1/4 of cases, I can again ask the question about level 2, where of course you'll recall this 10 is 3 plus 7. And we've dealt with the 3 already, that was those there. So the question at level 2 is it one of these 7? Or is it not? Ergodic principle, probability 1/8 that it's not. So if it's not, then we had a 1/4 first to get to that stage. And
Sorry, why is it an 8th and not a 7th?
Well, it could be any of them or none of them. That's 8 possibilities altogether.
Oh, quite
the
so.
seven,
Yes,
the 7
okay.
possibilities and missing out. And then at the next stage, where the 137 is 10 plus 127, the probability that it isn't there also would be 1 over 128. Oh, you can't do that on this, can you? 128. And now the probability then that it isn't at any of these levels, but is at the top level, is the product of those 3. Usual probability thing. And so the probability that by good fortune the artificial constraint which I put on is satisfied is 1 minus that. Okay, because that's the probability that the constraint I put on was failed to be satisfied. So 1 minus that is the probability that it is satisfied. And then that means that my original estimate of 1 over 137 for any particular element being picked out has to be modified, because it was 1 over 137 given my artificial constraint. But if I don't put that artificial constraint on, then I need to have the 1 over 137 multiplied by the chance that it is at one of these three levels. So I have a 1 over 137 into 1 minus 1 over 4 times 8 times 128. This is my second order calculation. And of course, you realise at once that the fact that I've got numbers of this order down below depends very heavily on your totally different calculation. I mean, that's how one... But I view that as not necessarily putting on any blame on you for this, but on the well-known fact which applies to me and I think quite a number of people, that you can't do any combinatorial calculation unless you know the answer first. Once you know the answer, then you can find ways of putting the numbers in. But if you don't know the answer, you're... So, well, I mean, maybe I shouldn't say that when the cameras are running. Anyway, so you then get 32. Now, as a mere piece of arithmetic, you can turn all this upside down with a bit of binomial theorem and say, well, it's 1 over 1 something a bit more than 137. 137 into 1 plus 1 over this. 2. And that, I think, comes... the 137 then becomes 137.033, which isn't very good, but it's improving. So that's that I see as a second order.
You have to know when to stop this, clearly.
No, pardon? Know when to stop? Oh well, yeah, sure, but
Sorry.
no, okay, yeah. So now I go on to the third order calculation, which is simply to notice that the assumptions which I made in this second order calculation aren't wholly correct. And so maybe people who are well informed like you have been looking worried already because you could see I was doing something wrong. But I think probably in putting it over to people who are not so familiar with the hierarchy, this is a reasonable didactic way of approaching it. I mean, the whole problem is this 128. I mean, maybe you see other things which are incorrect, but they are things which are incorrect in principle. But this is simply a bit of trouble here, because the 128 derives from there being 127 DC subsets at that level. And we've got to remember the ergodic principle, which says anything is possible. Anything which is possible will happen, and with an equal probability. Will there be 127 DC subsets generated through the hierarchy process by the 7 elements at this level? Answer is mostly yes, but not always. And so I had to do a bit of arithmetic to find out. I have to look to find what the answers are because I can't remember them. The point is, to put it in terms of vector spaces, if the 7 elements at this level generate a vector space of dimension 7, then those 7 elements generate 127 DC subsets, and that's fine. If 6 of these are linearly independent and the 7th is not, so we say the vector space is dimension 6, there are fewer DC subsets. And so on for dimensions 5 and 4. It turns out, just as a matter of fact, that you can't have dimension lower than 4 because of the nature of these 7 things. So that's something. Now I proceeded initially in the stuff that you were sent on a false assumption, and I'll just mention that in case you come across it again and you know, I'll tell you what the mistake was. I supposed that if the dimension was 6, the number of DC subsets would be 63. If it were 5, it would be 31, and if it would be 4, it would be 15. This is all 2 to the n minus 1, the usual calculation of numbers. This turns out to be untrue. And this was a surprise to me that I hadn't known this about the hierarchy before. I mean, suppose you have n independent elements, then they generate 2 to the nth minus 1 DC subsets, and they also generate, by their additions, 2 to the n minus 1 elements altogether, including themselves. Those two numbers are equal. When the original elements are all linearly independent. If the original elements are not linearly independent, then you still, I mean, suppose that k of them are linearly independent, then you still get 2 to the k minus 1 new elements, but you get more DC subsets than that. So it's necessary to know how many DC subsets you get in the various cases. So let me just tell you what the result of the arithmetic is. The number of ways in which you can proceed from this level to the next, what in my unregenerate days I would call the number of choices of 7 elements here. I don't know, I mean the number, well, choices is all right. The process chooses, and it does one on it. There are 74,088 of them. And a majority of those are linearly independent sets, and so give rise to the required 127 DC subsets at that level. But that majority is in fact 61,772 of them give 127. The others give less, and I mean, I put this in writing in the year before last at ANPA. I got the wrong answers then. I've since got a number of wrong answers. I now have got the right answers, I hope. And I had to do it by a rather roundabout way. You see, it's not difficult to find out how many of these possibilities give rise to a 4-dimensional one. In fact, there are only 2. So that's easy. And even the 5-dimensional one is quite easy to nail down. There are 300. But the question of how many of them are 6-dimensional is much harder to nail down, because there are rather a number of different ways of being 6-dimensional. That is, there are rather a large number of different ways in which the 7 elements can fail to be linearly independent. The last one could be the sum of 2 of the others, or 3 of the others, or 4 of the others, or indeed it could be worse than that. So I had to do the calculation a different way. What I did was to work out all the possible, well, I didn't do the working out, but I had to consider all the possible additions of different elements in the thing, and sometimes these additions will give rise to a 0. And then I counted the zeros. As I said, it's a countryman's method of counting sheep. You know, you count the legs and divide by 4. I counted the zeros. As far as the 6-dimensional cases are concerned, a 0 corresponds to a 6-dimensional case. That's fine. If it's a 5-dimensional case, there will be 3 of the zeros will correspond to each 5-dimensional case, and for the 4-dimensional case, a group of 7 zeros corresponds. So if you know how many 4 and 5-dimensional ones are, you subtract 7 times 1 and 3 times the other from it, and what's left are 6-dimensional. So this 61772 splits up into some 4-dimensional, some 5-dimensional, and some 6-dimensional. Now, the other thing I did, which was wrong in that calculation, was to take an average for the number of 6-dimensional cases. I took the DC subsets to be 63 in number, and then 31 for the others, and 15 for the 4-dimensional case. I did this because I believe that was so at the time I wrote it, still in my unregenerate days. Took an average and said that average will be what I ought to have put in instead of 127 here, and then add 1 onto it for that, and that gives a very much better value for one. In fact, it gives a value nearly as good as yours. Unfortunately, that good value is simply got by doing 2 wrong things which beautifully cancel out. So I now have to explain what the right thing to do. What it does show, that taking the average, it does show that the 4 and 5-dimensional cases have very little effect on the final result. They could make a difference of 1 in the 4th decimal place of the 137. And as I'm only worried about the 3rd decimal place, I'm not up to there yet. So what I have to do is worry only about the 6th-dimensional case. Now, how many DC subsets are there in the 6th-dimensional cases? Well, there could be different numbers depending on how the 6th dimensions arises. If the 6th dimensions arises because one of the 7 elements is the sum of 2 of the others, the number of DC subsets turns out to be 79. If it's the sum of 3 of the others, it's 95. So, I mean, these numbers aren't of great interest, but if it's of sum of 4 of the others, it's 107. If it's 5 of the others, 115, and if it's one of them is the sum of 6 of the others, it's 120. So those are all different possibilities which would arise, and so what one's got to do in the original arithmetic is to look at the zeros and see how many arise through adding up 3 elements, how many 4 elements, and so on, up to how many adding up 7 elements. So there's a lot more numbers come in at that stage, and one will have to feed that into the calculation. But the other thing, so that's one thing that was wrong in the approximate one. But the other thing that was wrong is to take the arithmetic mean of all these things that I'm working out and then add 1 and put in its reciprocal. Because obviously what one ought to do is average over all the possibilities. So in other words, one should take each of these, add 1, take its reciprocal, and then average that according to the number of times which it occurs. In other words, take a weighted harmonic mean of these rather than the arithmetic mean. So that's what I've done, and when you do that, you find...
Sorry, I'm very sorry, I missed why it should be a harmonic mean.
Well, because it occurs in this formula. Well, let me put it here. The thing we're talking about is altering that 1 over 128, which comes in there,
yes,
and saying that in 200 and something of the cases it should be 1 over 79 plus 1, and in some thousand of the cases it should be 1 over 96, adding 1 onto there, and so on. And so what one should do is to take, of course you've got to multiply by the number of cases, but you have to say, well, this modification here arises through 1 over 80 in 200 of the cases. It's 1 over 96 in 1,000 and something of the cases. And so taking an average of those, I'm not contending actually that doing that will give you a completely correct answer. I think really what one's talking about is a rather complex double probability distribution, and I'm taking a shortcut through. But what I'm do see now clearly is that to take the shortcut by averaging those numbers and then turning them into reciprocals was the wrong thing to do. So I do the reciprocal, and the add 1 and take the reciprocal first and then average afterwards. And the answer that comes out from that is 137.035. 0.0351 actually, just to so I'm certainly not right yet, but I'm some way on the way. Now, that's been derived by looking at the 6-dimensional cases. I don't look at the 5 and 4-dimensional ones because it's too horrible, since the number of ways in which a thing can be 5-dimensional, you see, for example, suppose you have 7 elements and it's a 5-dimensional space. That means 2 of the elements are sums of the others. Just consider the very simplest case in which each of those elements is the sum of 2 of the others. Even then there are 2 possibilities, because those 2 others may have a common element or not. And if it's the sum of more
than 2 of the other. You know, oh, it's just awful to look at all the possibilities. But I rely here on the fact that the 4 and 5 dimensional cases contribute very little to this, and so it'll be the 4th decimal place only which can be altered by them. So what I have looked at since, I'm nearly at the end of this peroration and we can then discuss again, I've looked at how one might look at something to do with the way that the number of DC subsets in the 5-dimensional cases is increased, and make some approximate calculations. And one way of doing this, I won't go into the details about this, but one way of doing this, jack this up a bit so that this this point 401 became 4013. Well, that's not very hopeful, but and what I've also determined is, you see, the number of DC subsets at any level here gets up quite high, but what it cannot do, obviously, is quite get up to 127, which would be the number if they were all linearly independent. So one could say, well, then at level 5, the best you could do by bringing in level 5 as well wouldn't be as good as if at level 5 you actually got 63, the boundary which you can't quite reach. So if you put 63 for level 5 and 31 for level 4, that would be a correction which you couldn't possibly hope to achieve that way. And by plugging that in, you then get, you get quite a big difference actually. You get 0.0354. So that's the end of the road for that particular correction, and it's obviously not far enough along the road to get the right answer. Okay, now I think I can sit down now, but I've just got a little bit more to say about that calculation. Naturally, I turn my attention then to thinking, well, why haven't I got the right answer? You know, for one thing, having gone through this rigmarole, which could have taken all sorts of wrong turnings, and finished up with something which is only in error by 1 in the 3rd decimal place, I naturally have an enormous personal conviction in its essential rightness. But the error of 1 in the 3rd decimal place is a serious error which must be compensated somehow. The way that I'm thinking at the present, but if you meet me in a month's time, I may not be at all, is this, that one has still, in this analysis, I've got over the artificial constraint which I originally put on to say, well, suppose it doesn't go over level 3, that the probability correction has taken care of that. But I'm still not asking any questions about how the process actually proceeds and how it knows, for example, that it's got 79 DC subsets when it's in that particular mode. And that, I think, moves me back to something which I discussed a long time ago with Ted, but which has rather got left out. That is, we're here talking about a very abstract representation of the process, and we do say these things like, well, there's an ergodic principle, it may change level, it may not. We don't go into any details about whether the thing wants to change level. I mean, if I may, I mustn't use those sort of words, but at one time, Ted used to say things like, well, there could be a rule which said that when it had got the same, all the same elements, it wasn't getting anything new. If it hadn't got anything new for 50 moves, it would decide to
like
increase it on the basis of chess, you see.
Right.
Well, that may be a way of thinking which at the time seemed all right, but seems more naive than is appropriate to our present situation. But at the same time, it does look as though I'm reaching the point where it begins to be important to start asking questions about the detail of the process instead of the whole abstract thing, and say, well, and I say again, how does it know it's got 79 elements? And I've done a bit of back of envelope work on how it could know a thing like that. It seems to me it could only know it by comparing the number of new elements it's getting with the number of old elements it's getting. And once the number of old elements is rather large and the number of new ones seems exceedingly small, it knows it's getting somewhere near the end, and it could make estimates of how far away the end is. Now, if it did that, these estimates could be at fault for a following peculiar reason. When you get those 79 DC subsets, instead of the 63 I thought, but a better way of thinking about it would be, instead of the 127 that 7 things ought to give you, how is it you're only getting 79? Well, you're getting some of them twice. In fact, it's much worse than that. You're getting most of them once, and some of them 8 times. And if some of them are coming 8 times and some only once, then any statistical calculation about how far you've got to go based on how many repetitions you've got is likely to be thrown out. And that would mean that you tend to underestimate all these numbers. That when you were in the 79 situation, let us hope, you might think it was more like 73 or something like that. But I can't put any details on that. But at least that would produce a correction going in the right direction. It would move it up to somewhere near 036.
Yeah, I have a couple of problems with the approach, and I'd just like to hear your response or explanation. I'm saying I'm not hard set on them, but the first one I think is probably the more serious. And the second one is perhaps a bit more formal and might be overcome, and I could just be wrong-headed about it. But the first one is that there's no physics in it.
Right.
And this is a long way to go when there's no, I don't see any reason why, for instance, we would get this particular fine structure value compared to one of the other values. The fine structure constant in ordinary parlance is a running coupling constant, and so there are different orders. So as you change energy of the system, you get a completely different number, or not a completely different number, but the number changes as you go up in energy. And so anything that's beyond the 1 over 137, I've always felt fairly strongly must have something in it about the physics. Some of these constraints that lead to the reasoning have to be on physical grounds relating to the particular kind of measurement that you're doing. And I don't see anything of that nature here. This seems rather absolute to me.
Let me ask you, because I could be ill-informed about this, but is it really the case that the running values of 137 affect those first 3 decimal places?
No, they don't. They affect the 4th.
Yeah.
But what you've been looking at here is only so far is only affecting the fourth. I mean, you know, that's
Yes,
you
sure.
haven't been affecting
Sure.
the third.
I see what you mean. Yes, yeah, I'm in difficulties there.
Yeah.
If I had finished up with .036,
then I would be much happier.
Yeah, I see.
Yeah, if that were really a hard and fast
and
number.
what I've got to, I think I can probably get round. I mean, yours seems to me the sort of difficulty that one could get round, although it seems like cheating. I've got to say that fourth place is part of my calculation.
Right.
It doesn't purport to be related to the fourth place of the measured things in particular
Yes,
experiments,
yes,
but it necessarily comes in calculating the third place. But I think what I'd want to take. Do you want to have
well,
the
actually,
other
I want to make the situation a little bit worse before we try to tackle it. You're using an awful lot of structure within the hierarchy to get the to get something out to the third place. This is actually fairly. Gosh, I think if I don't know how you do this in combinatorial terms, but if I were doing this in an ordinary analytic type computation, I would say this is probably a third or fourth order type calculation. I've really gone down quite deep into the various relationships that can exist. They certainly aren't the first ordered set of relationships of 3, 10, 137. They certainly aren't even the second order, because you've already gone at that with the 1/4, 1/8, 1/28, assuming that you can do that. So it's certainly beyond what I, at just a quick stab at it, would call a second order combinatorial calculation. And that worries me, because...
You mean it ought to be better for that much effort?
That's right, yes, yes. And if indeed the fine structure constant is tied down once and for all at 137.036 to 3 places, then we've got an awfully long way to go searching for structure in the combinatorial hierarchy to be able to account for
the other point,
for the other changes. Yes, right.
I see. Yeah.
And so that really worries me.
Yes, that is worrying. I agree. I'd like to take on the earlier point you made, though, about not seeing the physics in it, because I reckon that that's I think, well, no, I think that is unfair. I am arguing that the 137, to start with, having been identified as a scale constant, I then know that factor that I happen to have written as 1/137 is a good approximation to E squared over H cross C. So that's the physics. Right. Now the additional factor relates to the hierarchy and the process of determining these things in an abstract way, it's true, and to the probability of being at these first 3 levels. So, I mean, surely I don't need more physics than that.
No, that is what I was saying, though, is that it's not the 1/137 that obviously the physics
you
is
want
there.
Physics in the other bracket
yes,
as well.
Yes.
Oh, right.
Yeah, I think there has to be physics in the correction, and very serious physics, because we don't, unless there's some fairly serious physics in the experiments that lead to 137.036, we don't get 137.036. We never see that detail.
Yes.
And it's the precision of the fine structure constant that we know is directly related to the complexity and precision of the experiments that are done. And so any correction should mirror that process. You should be able to have some relationship between the experimental picture, so to speak, and the kind of correction that you're doing.
Yes.
Because if I go back to the earliest computation of the fine structure, I certainly would have no reason whatsoever to ever worry about anything beyond the decimal point, and therefore no reason to be concerned at all with this kind of a correction factor. And what's worse then is that the experiment would not agree at all with the situation, with the computation. Even if you just picked 1 over 137, you'd still be in trouble. Right?
Yeah. Oh, sure.
Yeah.
Yeah.
So, let me, while you think about that for a minute, let me hit you on the other the other point,
Yeah.
because this one maybe we can do away with, and then I can forget about it.
Yeah.
Which is, I was disturbed by the multiplying of 1/4 times 1/8 times 1/28, because to me you shouldn't be multiplying those under any kind of claim that they are disjoint probabilities, or that they're independent statistics for that matter, because in fact the 1 in each of those is a complement, and they're not independent complements. In other words, at the 1/4 comes from 3 plus 1, but that 1 refers to the 10 and 120, or pardon, to the 7 and 127 in the other two levels. Conversely, the 1 that's added to 7 at level 2 refers to the 3 and the 127, and so on. So they are.
No. This is not quite the. I mean, it may be you may be pointing to something wrong, but what you've said is not right. But I see what I haven't said in the exposition.
Okay.
I'm envisaging looking at an element and asking in succession whether it's at the first or the second or the third level,
Right.
or the fourth,
Right.
in that order.
Right.
So when I do it at the first level, there's a 1/4 of a chance that it escapes, as
Right.
it were.
Right.
And in that 1/4 of chances, I can say, well, now maybe it's at the second level. So at that second level, there's an 1/8 of a chance that it will escape.
But that's where
Yeah. Now.
we part company at that point.
Yes. Right.
Because you've already asked part of that question. Which means that you
no,
mustn't
I haven't.
Oh.
I don't think. Well,
Yes.
I mean, maybe I have, but
Because you've already asked. You're asking again whether it is the 1 extra includes the 127 again.
I
You're
see
saying
what
it's
you're
not
saying.
here. You're successively narrowing down. It's like doing a binary search almost.
Well, a
Right,
sort of,
in
yeah.
the sense that you're saying, well, it's we've got these things all stacked up, and so here's the 3, and then 7 more, and then 127.
I see.
Say,
Yeah.
well, no, it's not here. It must be out
be
there.
further along.
And so I move along out here, and I say, well, it's not there, and so it must be out there, right?
Yeah.
But you see, I've said twice now when you multiply them, but because you've got a 4 and an 8 in the bottom,
Yeah.
twice I've accounted for it being out there on the other side of the 7.
Let me, I see the picture which you have tends to support what you say, so let me draw the picture
Okay.
that I have.
Ah.
I looked on the decision, the probability, I mean this is as it were an argument entirely in doing a sum in probability, isn't it?
Yes.
Okay.
Yes.
So I looked on it like this, that you start off with the thing, you don't know anything about it. Now, in the first level decision process, here are the 4 possibilities. That is, it's either 1, 2, or the other one which is called 1, 2, or else you go on to the next stage. Okay? I mean,
Right.
it could be any of these, or you go to the next stage. Now, at the next stage, and this is where you're looking at it somehow differently from me, I think, that this next stage there are 8 possibilities. The ones that have got the numbers attached, or going on to the next stage. So having reached there in a quarter of the cases, we will now actually get to here in 1/8 of those quarter. I mean, maybe the difference between us is some sort of difference of prior probabilities, because I think this is because if it's bound up in the picture one's looking at.
It is. It has to do with how we're conceiving of the population in the first place. And I'm conceiving of the population as pre-existing. And the picture you've drawn doesn't look at it that way to me.
No, right.
And in fact, it bothers me that it.
I'm looking at it as a cumulative decision process.
Right.
That's right.
And yeah, and I have trouble with that if we're also then going to analyze the discriminantly closed subsets in the way that you have.
Oh.
Because they assume relationships between the levels. Remember, you had said earlier that that you had level indifference.
Yes.
But this decision tree doesn't
take account of that at all.
Right.
Right. Well, I must think more about that one, because what it could be would be that the difference would be the difference that I'm looking for.
Yes.
Or of course it could make matters worse. I'd like to turn your question about the physics on its head with regard to your calculation on which I model this. Now, why did I go to the trouble of constructing a different calculation from yours? Well, because I couldn't understand yours, no matter how I tried. And so, can I ask, where's the physics in yours?
Yeah, sure. The physics comes in straight up front in the form of the correction. The basic idea is that the fine structure comes about from, let's see, I think a small picture might help. We measure some peak, some frequency, and looking at the fine structure, we find out that in fact there's a double peak there. Right? Off of that initial peak, there's a plus bit, or a minus bit, however you wish to do it, and a plus bit. Okay? So that I have a term, if I normalize it, that looks like a 1 plus and a 1 minus. Some fact, well, it should have been, I'm trying to do an epsilon there. Okay, so we have two terms like that off of this primary value. Let's call it an f times. I'm not drawing that very big, but that's the rough idea. Okay. So that the point was straight up front that there should be some correction based on going from this central peak, which would give us this kind of a value, which is the Bohr atom, going to the Sommerfeld atom, which gives us, which is actually due to measuring, and this was prior, the experiment is prior, in which we see a splitting of this peak, of these measured values. So that it leads us to, in effect, if we were to just simply take it at face value, it really leads to two values of alpha, right, not one. Okay? And so it's not appropriate to say that this is due to an averaging of these. That's not what in fact is happening. And when you take the measurements, what in fact you have to do, because of the picture of the atom at that time, namely in terms of the analysis that led us to having something which called the fine structure in the first place, it meant that this was the only term that really was used in the computation.
Yeah.
Okay. And again, because of the model that was being used, it had to be this term squared. Okay?
Right.
Right? Okay, now, the way in which I came about this thing, which, by the way, this picture of the hydrogen atom and its relationship to the fine structure came first. Then came the fine structure computation based on this. And so then I began looking at what that should be, right? And my reasoning was based upon then on this whole ordering operator business. But so the idea was that, all right, we have, in this picture, we have a single ordering. We have, that is to say, a sequence of events, combinatoric events, that are repeating in some way. And so we would only get this thing, and that fit in with Pierre's pairs, 137 pairs, and so on and so forth, in the QOM event definition. All right. So that was all fine. That was a nice relationship between the 137 and the Bohr atom picture. The obvious then move away from that was to understand this. You may recall in my way of looking at things, when you take a value, you're always talking about things that could be treated as frequency probabilities, as ratios. Right? Always. There's no difference between some metric value and a probability, okay, a frequency probability. So I was still looking at it in those terms, saying, all right, what is this thing that is, what could possibly modify this? Well, clearly we have two different measures. There is some sense in which one of them is different from the other. What are the ways in which they can be different? They can't be different in terms of 137 versus 136. That's the cumulative, right? It can only be in terms of the 127, at the highest level of approximation, the 127 versus 126, and so on. Or it could be 127 versus 125, and so on.
Oh,
and
yes.
Backing on down from that, right? So I picked the first one and tried it, right? And my reasoning was, well, it's not, we can't talk about just the 127 per se. They have to be given labels, right? And the 2 and the 15 came from labeling these things. The 2 came because it's two of these. It's not, there are two peaks, not one of them, right? And the 15 came from the labels that were available in the hierarchy at the previous level, right? So that's the way that was constructed, and it just so happened. Then I called up Pierre and I said, well, this, read me off the value out of the particle book, and he did, and I told him what I had just done. I said, now, do you have a calculator? I didn't have a calculator at the time. I said, run this through your calculator, and what do you get? And then that's when he measured them and found that they came out the same. So but the physics is in this idea of the splitting, that it's plus and minus a value, all right?
Okay, yes. I mean, that partly answers it. In fact, it points to one of those many uses that the fine structure constant has, in historically the first one.
Right.
And actually deals with that one. Whereas I've been trying to do a more abstract calculation.
Right.
Entirely in terms of the hierarchy.
Right. Well, it actually goes further than that. In looking, I went off and started in subsequent years, then started tracking down a number of the experiments. And most of them are this character. Now, there are a couple that aren't, and usually there's actually some quibbling about some of them as to whether or not they're on the cusp of a high energy experiment, a scattering experiment, and so on. And so it's they do in fact get different values for the fine structure when they're computed that way. But it's almost always the case that regardless of the system that is measured, it is a situation of there being, shall we say, a mean value that is split into two parts. And invariably, because of taking the square and throwing away the negative value, they end up looking at only the equivalent of having only one of the experimental values from the splitting of the fine structure.